Roger, standing by 113.
This crew are about to fly a Sea-King with a difference. The main rotors are made entirely of composite materials. The first test flight will be monitored by design specialists on the ground via a telemetry link.
Okay, we're just about to get airborne here, and the wind is 120 at 10, gusting 15.
Oh, Roger.
Okay, starting to lift the selector. 3, 2, 1. We're coming up to the end of the wheels. We're just about to get airborne now. Okay, we're established to the 10-foot hover.
Roger, and timing.
Normal, we've got about 70, 72, 102 rotor RPM. It's fairly smooth, it's all very innocuous.
Oh, Roger.
And moving out over the airfield.
Rather surprisingly, composite structures are not a new idea. 3,500 years ago, when the farmers of southern England were clearing the forest to build their first farmsteads, they used composite structural techniques. A reconstruction of one of these farmsteads is at the bottom of this hill. All composite structures have two basic ingredients, matrix and reinforcement. Here the reinforcement is wattle. Saplings are woven through rigid wooden poles driven into the ground. In Bronze Age technology, the matrix was daub, a subtle blend of mud, straw, animal hair and cow dung. When this mixture dries out, you get a stable and weatherproof structure. The other aspect of prehistoric technology relevant to advanced composites is this, weaving. Here, the latest computer-controlled air-jet looms weave fabrics for the aerospace industry from glass fibres. Why fibres? Well, it all began at the Royal Aircraft Establishment, Farnborough, at the end of the First World War. A materials scientist, A.A. Griffith, had discovered a way of making materials almost as strong as the bond between the molecules themselves. He found that by pulling very fine fibres of glass, he could make a material that had no internal faults. And this material, as it stands, is 13.5 times stronger than mild steel. During the early years of the Second World War, radar technology had developed to the extent that radar could be carried aloft in aircraft. The scanners were mounted under the aircraft and contained in a streamlined fairing. These fairings had to be transparent to high-frequency radio waves. The ideal material for this was found to be glass-reinforced plastic, the first major application of this material. Since the Zeppelin era, aluminium alloy has been a major material for aircraft structures, as strong as mild steel but 1/3 its weight. But reinforced plastics are 1/5 the weight of steel, 1/3 the weight of titanium. The fibres can be lined up with the applied loads and the thickness built up with extra layers of material to suit local strength requirements. The result is a component matched more closely to the exact applied loads than is possible with conventional metal construction. Amazingly, the next great development in composites was also to come from the Royal Aircraft Establishment, Farnborough. Because in 1961, just over 40 years after the invention of glass fibre, Phillips and Watt invented carbon fibre. To make carbon fibre, you take a relatively straightforward plastic, polyacrylonitrile, you pull it under a severe load, and while it's under load, you attack it with intense heat so that the molecular structure becomes graphitized. The base result of this is that not only is the fibre lined up with the load, but the molecules themselves inside the fibre are also lined up with the load. This gives you a material of great strength and great stiffness. Greatly enlarged, we can see individual fibres embedded in a rigid matrix. Since carbon fibres are 30 times stronger and 75 times stiffer than the matrix, we must choose optimum proportions. What does the matrix do? Well, it protects the surface of the fibres against mechanical damage, which might reduce their strength. It prevents crack propagation by keeping the fibres separate. And also, it provides a method by which the loads can be fed into the fibres and from fibre to fibre, thus turning a floppy fabric into a rigid structural panel. Now, the resin system we use in aviation is epoxy resin. And we use epoxies because they have low shrinkage, they have superior mechanical properties, they have good adhesion to the fibres, and they have good water and chemical resistance. Design targets for the Sea King composite blade were straightforward but ambitious. It had to be capable of replacing the metal blade without any modification to the rest of the aircraft. Primary targets were greatly extended blade life, improved damage resistance, and ease of repair. Blade design was backed up by an extensive program of structural testing. Basic material properties and blade strengths were determined by over 2,000 specimen results, 470 structural elements, and 60 full-size blade sections. This testing has confirmed that the safe fatigue life of a composite blade is at least 4 times that of a metal blade, with the potential for unlimited life. Structural testing reproduces the most severe loads produced by manoeuvres such as flaring to hover, highly banked turns, and recovery from sideways flight. The 70,000 square foot composites production facility was opened in the spring of 1985 and cost £6 million. By extensive use of the most advanced production technology, a workforce of 100 personnel can build 40 blades per month. Sea King composite rotor blades were the first components to be delivered from this facility. Now here is a section through the Sea King blade. So let's look at the major components. We have the spar and the trailing edge. Now we'll talk about the trailing edge later. The spar carries the major loads in the blade, and the components that carry the most load are the sidewalls. So let's see how the sidewalls are put together. Layers of hybrid material are built up on a tape layer. Hybrid is a layer of carbon fibres and a layer of glass fibres pre-impregnated with resin and integrated into a single tape, a mixture which gives strength, stiffness and toughness. The tape layer is a robot railway laying down material from the roll. This material is only 10,000ths of an inch thick, and practical slabs of hybrid are produced by repeated runs of the tape dispenser, which can lay defined lengths under computer control, thus giving a sidewall thick at the root and tapering towards the tip. This machine was designed and developed within Westland Helicopters specifically to lay up composite rotor blades, offering uniformly high quality and lay-up speeds impossible to achieve manually. In many ways, the most complicated piece of the spar is the nose moulding, this elegantly shaped item here. And this is produced in unidirectional glass. So let's see how we make the nose moulding. After layers of unidirectional glass prepreg have been tape-laid into a 30-foot-long pack, it is slit into accurate widths and located into a press tool. The nose moulding elements are carefully positioned, building up the nose moulding profile. The final shape is produced by closing the two-part tool in a cold press. And the remaining unidirectional glass piece in the blade is the back wall. Let's see how that's made. This is similar to the nose moulding and follows the same sequence from tape-laid glass to pressing to shape. spar wraps are cut from unidirectional carbon tape. These wraps are positioned at 45 degrees to the spar axis and carry the principal torsional loads within the spar. Having made all the spar components, they are then assembled around a metal mandrel on the outside of this rubber mandrel bag, which is inflated to force the composite into a female mould profile. Ends of the mandrel bag not constrained inside the mould are trapped under metal shields. After cure, the bag is deflated and the mandrel withdrawn, leaving the spar hollow. The first material to be assembled around the mandrel is the inner carbon wrap assembly, with the fibres at 45 degrees to the mandrel axis. Before wrapping, the back wall has been located under the mandrel between the inner and outer wraps. We achieve a subtle blend of strength and damage tolerance by mixing glass and carbon in a variety of fibre directions. When the inner wrapping is completed, the hybrid sidewalls are located in place. The pre-shaped nose moulding is positioned at the leading edge. The outer diagonal carbon wraps complete the spar structural assembly. The hybrid sidewall is interleaved with woven glass at the root to give added support to the cuff joint. The wrapped mandrel is located in the spar tool and the upper half closed. The carbon, glass and epoxy resin is about to undergo an irreversible chemical change. The press control room starts and monitors the computer-controlled cure cycles in the presses. Heated press platens take the tool and composite to 75 degrees C. At this temperature, the resin system reaches minimum viscosity and the mandrel bag is slowly inflated to 200 psi, forcing the composite into the female spar mold profile. Then the press is taken to 125 degrees C for a curing dwell of 80 minutes. When the cycle is complete, the spar is inspected for wall thickness and structurally examined by radiography. X-ray examination of composite materials is a new science, almost a new world, like TV pictures from Mars. Here in this early trial specimen, we have included a tiny particle of metal which glitters in the X-rays like a cut diamond. The dark, irregular shadows along the top of this trial spar reveal a wrinkled nose moulding. All spars are scrutinized in this way, and thus we have a high confidence in our quality standards. The trailing edge comprises two woven glass fibre skins bonded to a honeycomb core. Now the honeycomb supports the skin over its whole area and also serves as a shear connection between the two skins. Finally, the shear connection is made between the honeycomb and the spar rear wall at this layer of foaming adhesive. The spar is loaded into the trailing edge assembly tool, locating on temporary alignment plates. trailing edge assembly begins with a foam wedge at the root end. This is followed by sections of honeycomb, which are located against the foaming adhesive strip along the spar rear face. The honeycomb is slightly oversized to produce a pressure at the honeycomb to skin interface when the mold is closed. The woven glass fibre skin has epoxy film adhesive on the inner surface. 1 hour at 125 degrees C cures the adhesives. When cured, the blade must be thoroughly inspected for bond integrity. Thermography is a method of non-destructive testing. Hot air blowers locally raise the blade temperature by 10 degrees C. An infrared camera observes the blade temperature. Since voids and D-bonds offer poor heat conduction, they can be detected by their different color temperature. After this inspection, the leading edge erosion shield assembly is bonded to the spar. These 4 replaceable titanium sections protect the composite spar from erosion damage and give a conductive path for lightning strikes. The erosion shield assembly is bonded to the blade in a microprocessor-controlled rig. When cured, the bond is checked by thermography or, as here, by an ultrasonic signal passing through a transfer gel. The presence of a void or D-bond changes the signal sufficiently to detect the defect. Our confidence in the integrity of bonded joints is based on this extensive and detailed inspection. To resist high bolt clamping loads at the root end, we insert a filler plug bonded in with a robust filled epoxy. Stainless steel shims are then bonded to both faces of the blade. These protect the composite from fretting contact with a bolted steel cuff and must be very flat and parallel to each other. Next, we drill the root end holes using a specially developed carbide-tipped air-cooled drill. A numerically controlled drilling machine is pre-programmed to drill the complete hole pattern to a close positional tolerance. Hole accuracy is such that no reaming is necessary, and the entire drilling operation takes only 15 minutes per blade. The composite dust is removed by an extraction system. Laminated shims pack out the gap between the bonded shims and the metal cuff, which is then assembled to place with its jaws held open. This cuff enables the composite blade to be bolted to a standard Sea-King hub and is machined from the same steel forging as used on the metal blade. Half-inch diameter bolts are wet assembled with jointing compound through steel bushes bonded in place to protect the joint from lightning strike damage. The tip balance weight assembly is bolted to 2 U-shaped brackets, which are held on by single side fasteners. They are located by shims bonded to the inner face of the spar. Although major items have been weight corrected during manufacture, the final correction is by 2 rows of heavy metal washers positioned to allow both span-wise and cord-wise weight adjustment. If blade tracking adjustment is required, then the trim tab angle can be altered to suit. Trim tabs comprise 2 aluminium alloy plates bonded to each other with epoxy film adhesive and to the composite trailing edge with contact adhesive. Both adhesives are cured in one operation by local application of heat and pressure. After applying a white epoxy primer, the blade is polyurethane painted. The closed tool technique offers a high profile accuracy, checked on every blade by this computer-controlled coordinate measuring machine. The sophisticated measuring head floats along a 10-meter-long granite block and is accurate over the entire blade length to 2 microns. Fine adjustments to the blade static balance are made on this rig. They are then whirled to match a common interchangeability standard, making not only final dynamic adjustments, but also setting the trim tabs for uniformity of aerodynamic tracking. Now let's take a look at composite rotor projects beyond Sea-King. New rotor shapes, which are impossible to fabricate in metal, promise spectacular increases in stability and performance. Extended tip configuration gives much improved rotor performance, leading to higher payload capability. It offers lower power consumption at high forward speeds, combined with improved high-speed stability and control. Computer drafting systems can provide a very accurate three-dimensional definition of even the most subtle changes in section. Once defined, this geometry can be automatically translated into a set of instructions for the microprocessor controls of a multi-axis cutting machine. We have now produced a precise replica of the computer geometry. The new blade geometry is a fundamental ingredient in the Anglo-Italian EH-101 design. Blade structure has been modelled using Nastran finite element techniques, broken down into an intricate lattice of individual mathematical elements, each element representing the properties of the composite material it replaces. Apply the flight loads and you can observe, greatly magnified, the blade bending and twisting. EH-101 blades further integrate shape and material. Computer-generated patterns are checked against a development tool. The ability to tailor composite materials into the most elegant of aerodynamic profiles is fully exploited. The Sea-King blade has now been brought successfully through all development stages and is now in full production. How do we control such a complex production process? Our answer is to develop an integrated systems approach. Remember that all major operations in the production and inspection sequence are controlled by computers. We've already seen them at work controlling the tape layers. Monitoring the cure cycle in the presses. In the examination of the blade interior and the dimensional checking of the blade exterior. All these devices are linked to a computer local area network, which allows access to any of these computers for data examination and analysis. We have chosen to control blade production using flow line techniques, rather like vehicle manufacture. The shop floor is divided into special work bays or areas. Each bay has a precisely defined task to perform in a given period of time. The distribution of all materials, part finished components and consumables is controlled and balanced. This is achieved by accurately measuring the work in progress levels daily at each bay. Deficiencies are identified by the computer, which either orders additional components from other bays or produces a picking list for the store's personnel. The local system also controls the store's inventory with particular regard to shelf life. Since the system is aware of current stock levels and anticipated build rates, production control staff are reminded when reordering of any material is required. Future developments include incorporation of a real-time simulation. Here, the shop layout and the total resources within it are being modelled in a variety of ways to determine the optimum throughput.
Rolling in now.
Roger, and monitoring throughout.
Stand by, 30-degree banks turn to starboard. Rolling in now.
The blade meets the design targets. The specialists are satisfied.
Okay, going off to the west end, and then we'll run down the airfield west to east up to 60 knots.
First production orders for the Sea King composite blade were received in May 1985, and that's just the beginning.